vehicular sharing systems. That work, as I said, it's part of the work that I initially started at KU Leuven, at COSIC. And I'm keep on working at NSS, at KTH here, because we're doing a lot of security and privacy protocol designs, at least my part on for V2X systems. So this is this presentation. Actually, I will try to split it in two parts. One is about such a system. It's complex, so we try to split it in a way that's okay. How we design a system, like the time of that we have, just quickly, the threats and the requirements that we need to consider. So when we are talking about privacy by design and by default, that's in a legal framework. We're talking in GDPR a lot about discussions. In practice, when we engineer protocols and systems, how we do that. Of course, this presentation will not gonna cover all the steps, but give a little bit of a potpourri, let's say, of the reasoning and thoughts. We're gonna talk about the current state of the art of the protocols that exist. And in the second part, I'm gonna talk about two protocols that we have designed. The first was at COSIC, the second is part of the first with more extended work. Now it's at NSS. So as I said, I will be asking questions, and if you want some clarification, please go ahead. The only thing, it's going to be recorded. So what is a vehicle sharing system? And essentially, to give a hint, it's a physical keyless. And what the systems are trying to achieve is to access a vehicle without the need of physical keys. All right, so that's simple as that. So we use digital keys. We can use our phone. We can use a smart card that we can access the vehicle. And the cool thing that we can do with that is actually dynamic allocation of the access, right? And we can give it to someone that we know, for instance, family members. But the challenging part starts when we will give to someone that is unknown to us. So I will show you a video. It's not advertisement, but it will give you a very good overview. I hope if you cannot hear, just tell me if you...
Volvo Cars is reimagining the future of driving. Imagine being able to leave your key at home and still use your car. With Volvo's unique solution, you can use your phone as the key to unlock and start your car using Bluetooth technology. But it doesn't end there. Volvo's phone-based app key means that you can actively share your digital car key with whomever you wish, as long as you're connected to them via your Volvo On-Call app. This means that your car can be shared without the need to exchange physical keys. In the same way, other people can also share their cars with you, or you use car sharing services when you need to, such as when you travel to another city or country. Simply book your car of choice.
All right, I think that's, we got a bit of an overview of how the system is working. Essentially, we have the phone, we dynamically allocate, we access the vehicle. And actually, the marketing department of Volvo, has done a very good job with this video. But it's not only Volvo who is working on that. Actually, there's a consortium of car connectivity. It's called of automotive industry partners, which is Mercedes, BMW, and more, who in 2017 released a white paper about how that would be a functionality on, of course, a high level, not a technical paper, on to unlock a vehicle and share. Recently, there is quite some activity from Apple side that they say that they propose the same functionality, with 2 patents, the one in 2016 and actually one month ago. One is called car key and the other one is called friend key sharing, which essentially they propose a protocol of how having your phone, you can add a key on your wallet in different, this is the Apple approach. And then you can share, you can distribute, you can dynamically allocate access to a vehicle to another person. All right. But as I said, these are very nice concepts. These are very nice services. These are very nice applications. But as privacy-savvy researchers, experts, practitioners who have to think twice and have to think twice on the challenges that we have here, on the challenges and issues from the security aspect, but also from the privacy aspect. And I'm going to give a quick overview of what are the potential problems. And here we can draw a simple sketch of a system with an owner and consumer having their portable devices, which can be phone, that they are accessing, they are communicating either between each other or with the assistance of a cloud infrastructure with a service provider. And that is communicating with a vehicle, and the vehicle is equipped with an onboard unit, which that onboard unit has the intelligence that would support this, facilitate this sharing. And that onboard unit can scale in hardware sizes from very small to fit in a vehicle, to fit in a bicycle or e-scooter that we see nowadays in cities, to bigger vehicles. So what is the first problem that's okay? It's a typical, let's say, security challenge that is a single point of failure when we have one server. There are many things that need to be done also that to patch vulnerabilities. So to safeguard the data from the database aspect, how you secure the credit cards. For instance, there was a leak of the data breach from Uber, and hackers got quite a large volume of data, like of users registered in Uber. And this is a problem that this is an essential problem that everyone who is building a secure infrastructure for the cloud is considering, from firewalls, from network tools, to how databases are secure, to web interfaces and services are prone against attacks like cross-site scripting, SQL injection, and so on and so forth. Another problem on the privacy spectrum is the fact of profiling. So these systems can feed the service providers, can collect a lot of information that essentially, as more you interacting with your system, it accumulates and it actually can deduce preferences for you, whoever is interacting with that system. From a simple, for example, rental time, duration, to where you are when you are renting, to, for instance, deducing whether you like luxurious vehicles, whether for a specific month you are renting a vehicle for disabled people or special needs because there was some XYZ accident. And there is no much, there are some research that showing the possibility of profiling of users, not tailored to vehicular sharing, but we can see how this problem can scale. For instance, there is a paper, and also Uber was trying to do the same by feeding the service provider with data from the location of where you are, how fast you're turning your steering wheel, your behavioral attitude on the road. It can deduce whether you're a good driver or not. So there is an automated processing whether you are a good driver or not, and then they could penalize you or charge you more or less. That's very interesting. And actually insurance companies, they try to do. And we have to say that GDPR is highlighting on this automated processing of the personal data. And there was another interesting research that some anecdotal evidence that in New York, the cab drivers, the taxi drivers, they could deduce whether their religious beliefs, because they could somehow find from the times that they were taking breaks whether they were practicing their religion. So to design such a system, we need to have systematically and holistically do several steps. And one thing that you need to do, of course, is to define the whole parties that are involved in such a system, the entities, or how we say it in engineering and computer science, the system model. Many times when we are designing a system, many times I have seen by reviewing many papers that, or many solutions, that the adversarial model is very unclear. So here I want to emphasize on the fact that the part of the security threat and privacy threat analysis is extremely essential to define in the first place what is your adversarial model, what can go wrong, what are you trying to solve essentially. And in the security world, in our security ecosystem, we talking about adversarial model and security and privacy threats, because it's so essential, because we're gonna to build a protocol or a system, you will build it based on that. So defining the adversarial model, defining what can be your vulnerabilities, and then how you're gonna essentially tap it, how essentially you're gonna provide solutions for that. In this work, we're gonna talk about the access token, essentially, how you can share access with dynamically share access. And just to give very quickly, of course, to do that, the system model, to extensive literature work and analyzing industrial systems and also research, academic papers. But moving to the threats and the adversarial model, there is some methodologies, at least to classify, to identify the classes of threats. And I can recall, although that I was not present, some presentations that with Lyndon, for instance, in privacy engineering, you have invited him in the past. So that's very nice. So probably the audience knows a bit what the Lyndon is. It's essentially a framework that you go and analyze, which can be your classes of threats and what this can happen, essentially, for that threat. And STRIDE is an OWASP framework that from the security spectrum. And based on the threats, you identify requirements, and then you work on the solution. So back in COSIC, we work on the foundation of how the system would look like as a system model. And I'm not going to go into detail, but essentially what we have here, we have users, we have the portable devices and vehicles with their own intelligent units, which are, we call them onboard units. A cloud service provider that would facilitate the sharing, but also in the play, we have to have authorities. And we have to have authorities because we have vehicles, there might be accidents, wrongdoings by users. And we have vehicle manufacturers, third parties, which are, for instance, insurance companies. And there are several operations in here that a system can support, from registration to booking. In this presentation, I'm going to focus on two papers related to vehicle access provision, but also you can have payments. But the interesting is that all of these and building a system supporting better saying access provision, access token generation, distribution in a privacy preserving way, then and you needing to support accountability in case of wrongdoings, it's a bit challenging. So we will see how we approach this problem alongside with other challenges that I'm going to mention. So let's give a working example. So we have an owner, Iraklis, and a Bob, are classic figures on security. They talk to each other, and then they define booking details like the availability. Let's assume that this booking is shared with the service provider, the cloud provider. The cloud, it generates an access token, a ticket, where Bob can take it and open a vehicle. So what can go wrong here? You can, I guess, identify, we have no crypto, we have no security right away. You can pinpoint like straightforwardly some issues here. That's what we call, it's a Dolev-Yao adversarial model, which they have defined essentially that an adversary can be sitting on the communication channel and can try to do any, it's an active adversary and can try with any possible means to either extract information or manipulate the data, manipulate what one client to the server is sending, or two parties are sending between to each other. And manipulating, replaying attacks, for instance, that's also, it's part of the adversarial model description. So the first thing that can happen is very simple as that an adversary can try to have information, to disclose information and tamper with data. So if we do this exercise of threats and requirements, we will quickly go and to see that, okay, this information is exchanged from here to there. We have this adversarial attitude, so we have these threats. So we need to have confidentiality, entity, and data authenticity. So just to put an asterisk in here, most of the times people are talking about integrity. In better terms, it's to say data authentication, to just in our nomenclature. So data authentication is to not avoid the tampering of the data. Entity authentication is about two parties authenticating to each other. All right, so another interesting aspect on this vehicular sharing system is the adversarial model now is, before it was outside of the system, let's say. Now we can have various types of adversaries, because it might be Bob that is within our system, is part of our system, can misbehave. So Bob might deny the fact that he used the access token. So we have clearly a repudiation attack. And in such a system, we will need to build it in a way to consider non-repudiation of delivery of the access token. That it's truly that the Bob is the one that, and also that has sent the access token and Max is the vehicle. A very interesting part of the challenge here is that the key of the car should be stored in trusted devices, in trusted entities. And the problem is that mobile phones are getting lost or stolen easily. So imagine that you have the master key of the vehicle on the phone and the phone breaks. Then updating the vehicle key might be not a straightforward solution on the vehicle. So some other party has to have not only Alice, which is the owner, and not only the vehicle, some other party probably has to have the key. And for sure, not Alice. And on the realm of privacy, one problem that it can happen is that the service provider can collect behavioral data, can collect sharing information, and then extract patterns of users, how, for instance, preferences of users. So we want to build a system that considers anonymity, for instance, of transactions, anonymity of booking details, anonymity of the access token, anonymity of user, essentially. And in this specific is Bob. towards an untrusted cloud service provider. Okay, so until now, in related work, state of the art, there are protocols. I'm not going to analyze this table, but most of the protocols are considering a trusted service provider. I'm highlighting two protocols, which actually, for the first time, they consider that the service providers should be considered as untrusted. We should do a protocol, we should build a protocol in a way that we still provide the service, but we will do it in a way that is the outsourcing computations will not be visible. The content will not be visible, not the computation per se. I said that I'm going to do some questions in the meantime, but I think that I start talking and I haven't. In that, maybe I will do a pause, and any question at this moment, someone has something to ask. I'm going to go a bit to some more technical. All right. So there are two works that me and my colleagues we have built it on this vehicular privacy preserving, providing secrecy, outsourcing computation on trusted service providers. That's called Kcar. The first, that was the work that happened in Kozik when I was a PhD student with Abdel, Mustafa, Bart Menning, Simen, and Bart Brunel, and now at NSS at KTH that I am with Dragos, Mustafa, Bart Menning, again, Bart, Brunel, and Papadimitratos, professors here. And the two protocols are relatively similar. It just, actually they are different, but they're high level, the protocol design is similar. That's why I'm gonna describe it as an all. And at the end, I'm gonna talk a little bit about the efficiency, because the problem is, aside of these problems that I talked about, security, threats, privacy, and functional challenges or requirements, when you build such a system, you want to build it that will support efficiency, that will support real world, that could be deployed in a real world setup. And you need to be efficient and you need to be scalable. For instance, not only have supporting a user with one vehicle, but it might be that there is a vehicle sharing, car sharing company that, to the analogy of car sharing company that supports, for instance, has 1,000 vehicles on their disposal. All right. So as we talked, recall the previous slides, there are several security and privacy requirements in this presentation. I'm going to highlight 4. And let's try to do it step by step. I'm going to start with a very basic protocol and then I'm going to build it up, and you can help me along the process. All right.
Iraklis, can I ask a question?
Yes, please.
Because you triggered me with the Hertz and Avis examples. Did you also consider availability as a threat? So, for example, denial of service attacks.
I can answer this question maybe. So this is a little bit, I would say, on the capacity of the system, not on the capacity. Yeah, it's it's a different type of threats, I would say. It's more on
Yeah, okay, so you're just focusing on the privacy parts now.
So the computations are important. So whether the servers are the processing power of the servers, but they don't have. This is let's say we are building at an application layer. We're building a protocol and a system at the application layer. This actually needs to be added very well, as you pointed, on the network layer. So you need to have an extra mechanism that is going to be, if we can think it as a modular Lego piece, that you need to add it. So this will work, and then you need to add this, some countermeasures, how you can channel denial of service attacks, or how you can block, you can have an extra firewall. Yeah. So it's, let's say, another module kind of
Yeah, okay.
complementary
Clear.
to this, but we focus that mainly on the application layer. So let's start with the beginning. That's the full picture. I'm not gonna go, I'm gonna go step by step. And first we know to do what? We have the booking. So two users, the owner, Alice and Bob, they have agreed on the time, the period, and where the car is, the location. Maybe Alice has multiple cars. So they have agreed on which car, which time, how long, and maybe also there's some geofencing, how far Bob can go. And let's build together a very simple way of sharing these booking details to the vehicle. So what we will do in a secure fashion, let's say the adversary wants to eavesdrop and read. So it Dolev Yao again, like communication channel, he wants to read, tamper, replay. So the first thing that we can do is I put it in a simple form. We can put any form of encryption that is symmetric key, because let's assume that the car has symmetric key capabilities. And what we can do is we can encrypt the booking details with the key of the car, create an access token, send it to the consumer, and then the consumer share it with a vehicle. The vehicle decrypts, and voila, the vehicle checks the booking details and authenticates, the consumer authenticates Bob and allows or not access to it. But that's a very simple protocol. We have the next question that comes to our mind, recall the four requirements. But what if the consumer misbehaves? What Bob is actually pretends that he never used the access token. Usually what is happening in these scenarios is we have a trusted entity, which this trusted entity actually is the one recording the transactions. And this trusted entity usually is it's a service provider. So it's our cloud in this specific scenario. And what can happen is we can do the same thing, but the access token now distributed over the service provider. So any wrongdoings by the consumer are actually recorded by the service provider. Now, think about the third problem that I told you about. The key of the car should be on a trusted entity. And it might be that the portable device can break. Car key revocation and update might be a very expensive operation. So we need to have the key on a service, on a trusted entity, the master key of the vehicle. And who can be? One is the vehicle itself, of course, because it needs to decrypt. But also the vehicle manufacturer, which is actually the one who is generating the physical keys. It can be the one who is generating the digital keys as well. All right. So by building this, by now adding this arrow, essentially I say that the key of the car is being shared, the master key, to the service provider. All right, that's really bad idea, but bear with me. It's not really a bad idea. Many solutions are using it, but I would say it's not the best idea. Bear with me, we will solve this problem in the next step. So what can happen is that now the booking details can be sent. That can be sent over a secure and authenticated channel. We can use, for instance, every channel now can be secure and authenticated using SSL TLS. We know what is SSL TLS more or less. So in every banking transaction that we do, in every secure communication that is established between ourselves, clients, and the bank servers, there is first a negotiation and there is first an establishment of a secure and authenticated channel using SSL TLS. Something similar we can use to mitigate Dolev Yao attacks, all right, to mitigate the communication attacks of active adversaries that I was telling to you. All right, so we share the booking details in a secure and authenticated fashion. The service provider, our cloud, received it. And now it generates the access token by encrypting with the key of the car, sends it to the consumer, and the consumer authenticates the vehicle, delivers the access token. The vehicle decrypts, voila, gets the booking details. and enables or not, depending on the booking details, access to the consumer. All right, let's move to the let's say challenging, cool thing of more on the privacy realm, how we can achieve anonymity. So how, before, recall that the booking detail, we send it to the service provider, and the service provider have, apart from the key of the vehicle, all right, they have also the booking details. So how can we conceal, how we can provide secrecy of the booking details? In this scenario, we don't want to learn, the cloud or the service provider, we don't want to learn that who is Bob, and we don't want to learn which car Bob is getting access to. The owner will be known to the service provider that's communicating. So how can we do it? All right. So as I said, the service provider wants to extract as much, is eager, and is from honest but curious, which means that is trying to extract as much information as possible to active adversary. So it tries to extract and learn as much of, and then all this information will do whatever it's on their business model. So we try to stop this. So one way to achieve anonymity is what we called utilizing secret sharing. So secret sharing is a concept. It's not a concept. It's a mechanism that, to say it in a very simple terms, that you take a piece of a text, you write your secret, you cut it into pieces, and you give it to different parties, X parties. In this specific case, for instance, 3. So you take the booking details, all the secret, you cut it into pieces. Each piece, we call it, is indistinguishable from randomness. It's not random data, but it's looking like completely random. So each server that will gonna receive the booking details, we're not gonna know. And just for technicality, both Alice and Bob, they create an authentication tag, and Alice is sending both their shares to the service, to the cloud provider. So the cloud provider, what it's doing is generating the access token, but as you see on the booking details and as you see on the access token, it's in brackets, meaning that they are doing operations over the untrusted service provider in a way that the service provider doesn't learn the secret, doesn't learn the content of the booking details, but it still does operations of encrypting the access token, encrypting the booking details, resulting at an access token with the key of the car. Now, as you see in the picture, the key of the car is also secretly shared. So with this, this operations over secret shared data is called multi-party computation, and essentially what we do here, as I said, we actually solve 2 problems. One of the key of the vehicle that was in plain text to the service providers, and one of the booking details, the keys that were both in plain text. So now both are in secret share form with the operations, we do encryptions, and when everything finishes, then it's called, we reconstruct the shares, we put the pieces all together, but we have done operations over the secret so that let's say the piece of the page is in an envelope. So we put this in an envelope, let's say schematically. This is being outsourced, submitted on a public ledger, think of like any simple database. And then the consumer, since they know the access token, the authentication tag, it can retrieve the access token. Now, this small little figure of the onion, it's actually, we can recall that it can be an anonymous communication channel such as Tor, which hides from the IP address from the public ledger, the IP address of the consumer. And now the consumer can send to the access token to the onboard unit. The onboard unit can decrypt and receive the booking details. So this is in a nutshell, the idea that we can do computations over encrypted data over over data that actually on an untrusted service provider. This is not on over encrypted data. We encrypt the data on using multi-party computation. So just quickly, I'm not going to go into details on this. So the key of the car is, as I said, in a secret share form, but and what is happening is that to retrieve the key, essentially we have a matrix, and then this matrix we can retrieve the key by doing some what is called a quality test. And we can identify it's an interesting part that's the bottom right, the Kcar, which after this operation, it's the one is the position of the key, but even the position itself, the number 1 or the zeros, it's actually in a secret share form. So essentially the server doesn't know even which record it is. So I'm not going to go into these technicalities. Because of the properties of the secret sharing, if there is a vehicle crash, incident, accident, something wrongdoing by the user, the servers can record, can store, and for this specific user, they can authorities can request and say, for instance, for this specific time, with this owner, please send me the record, the specific record, and they can reconstruct what we say the shares of the booking details by getting all the shares, right? So now this work, again, it's implementation and technicalities, a little bit on the processing power, but what I wanted to say here is that it is possible. We have the essence of this presentation and the essence of these numbers, of these schemes, is that nowadays we have systems, we have solutions that we preserve privacy, and then it's actually pretty efficient. That's the takeout of this. We can design systems that we might be compromising a little bit on time, but not to the point that we will actually see a major difference. And for instance, this table, what does it say? It says that we have a number of vehicles per owner. If we are feeding the system with 1,000 vehicles at the same time, and we do this in parallel processing, and this is only the service provider operations, how costly can that be? How costly can that be? And if you see the last line on the table of the CBC MAC, AHT MAC, I'm not going to go into these details, but on the throughput, the last on the right hand side, essentially it says how many access tokens we can generate, 32 and 84, and it's to the order of if we have 1,000 vehicles, then it's still all operations. If we think about them, including all steps, it's 150, 130, 140 milliseconds flooding the system, and for only the service provider, it takes 11 or 31 milliseconds. Actually, 11.9. That's the part of contribution, let's say. And we can think that the arrival rate of how many vehicles actually can, one thing is that from how many vehicles I can search, and the other thing is like also how many vehicles simultaneously someone can ask. So if on a peak time of the day, how many vehicles can be, for instance, at 5 o'clock or at 8, there is a peak time, and this peak time can be per second requesting 68 vehicles. The last person in the queue, how much would be affected? So all in all, on the service provider, it's going to be 8 seconds all in all, it will be 9.3, 9.4 seconds. So until the moment that you're going to register, go to the vehicle, 10 minutes, and this is not on the servers that are fully optimized. So this can actually parallelize the scale much higher. So what I wanted to say here is that vehicle sharing systems are complex systems, but we can still have nowadays solutions that they can provide us with the functionalities, the requirements that we want, the functionalities, and the security and privacy requirements. We need to design it very carefully, considering the proper adversarial model, the threats, and as I said, we have solutions that can facilitate services, for instance, but in a more privacy-savvy way, in a way that secrecy and privacy can be safeguarded, technically speaking. So that's all from my side, and I'm looking forward and happy to receive your questions.